Okay, YouTube, in this video we're going to introduce the concept of graphing complex numbers written in standard form, as well as talk about the parts of the number and the absolute value of that number as well. So we have graphical representations of complex numbers. The first thing we want to do is we want to recognize that a complex number, recall that we write it as this number that has a real part and an imaginary part. So we say z equals x plus yi, and all three of these numbers you see here are examples of complex numbers, but the first part of this, the real part, is always the real, the thing that doesn't have an I on it. And then this has no real part, it'd be 0 minus 5i, and then the imaginary part. So when it comes to graphing these things in the xy coordinate plane, we have the complex number plane is what we call this. And instead of the x-axis being some real number here, we're saying that this right here is the real axis, and that x is the real number part to this number. So we say that this is the real axis. And this is our, right here, our imaginary axis, or you could say like our y-axis represents the imaginary value of this, so the imaginary axis. So when graphing these numbers, to make it pretty simple, we say the number 3 plus 4i is where it is because we go 3 on the real axis, 1, 2, 3, and then up 4 on the imaginary axis. So it would be something like maybe this right here, or negative 2, comma 3i. We would go left 2, and then up 3 here. It would be negative 2, comma 3i. Or negative 2 plus 3i is this number here. And then last but not least, negative 5i. Let's just recall that that's the same thing as 0 plus a negative 5i here. So we would basically be going left and right none, and then down 5 from the origin. 1, 2, 3, 4. And that would be that number right there. So graphing these things are pretty simple to do in the complex number plane. What we want to do is we want to be able to calculate a value for this number, not just any value, it's absolute value. So recall that the absolute value of a number is its distance from 0. So when we talk about where is 0 or 0 plus 0i in the complex number plane, we would say that it's this point right here. So for us to graph a complex number such as 3 plus 4i and ask ourselves what is the distance from this number back to 0, what we could say is really that visually we represent it with just this line segment from this number back to the origin here. And the nice thing about this is, just like we do with vectors, this is very, very much the similar situation, we would say that we both know the horizontal and kind of the vertical components of this right triangle that it forms here. So if we wanted to find the absolute value of this number z, we're saying z equals 3 plus 4i. Oh yeah, that's another thing. We tend to write complex numbers with a z equaling some real plus imaginary parts. So if we want the absolute value of z, we could just write the absolute value of z this way. We could write the absolute value of z this way. But by definition, we say that the absolute value of a complex number is really just the hypotenuse of this right triangle. So more in general, we could say, given some number xy, x comma y, that represents some x plus yi is really how I should be writing it here. X plus yi, this number right here. We could say that we would know that this component is y in height and this component here is x in length. So we would say that this number right here, the distance out to z, I suppose we could say that this distance here, we'll call it d. We would say that that distance is equal to the absolute value of this complex number, but it really is just the square root of x squared plus y squared. So just knowing the kind of the horizontal and vertical components of this, we can say, well, the absolute value of this number here is equal to the square root of, it would be 3 squared plus 4 squared, positive 4 squared, positive 3 squared, and we would get this right here. We would get the square root of 9 plus 16, which in this instance, of course, is the root 25, and we say it's 5. Now, technically, plus or minus 5, but I am going to go ahead and say that since we're talking about the absolute value of something, the definition of the absolute value of something is assumed to be only a positive output, is a distance. So really quickly here, let's go ahead and find the absolute values of these other two numbers. For instance, negative 2 plus 3i. According to what I've said, it's the distance back to the origin, but again, this also casts a right triangle here where we have a negative 2 for a horizontal component and a positive 3 for a vertical. So its absolute value is just going to be no more than the square root of 2 squared, be negative 2 squared, plus a positive 3 squared. And so we get this right here, we get 4 plus 9 is root 13. So we say that this is the absolute value of the number right there, and we could say that this hypotenuse length is root 13. And then last but not least, the absolute value of any number that is purely real or purely imaginary. Simply put, we could say that this distance right here is 5 in length. Why? Because it's 5 units below the origin in the x or the complex number plane. But if we were to again represent this as a complex number in standard form, we have both the x component and the y component of this number. Nothing's stopping us from using this definition over here that says the absolute value is the x component squared. See, I'm thinking x and I wrote x, which is 0 squared in this case, plus the y component squared, which is negative 5 squared. So we get the square root of 0 plus positive 25, which is root 25, which again is what we suspected it to be, a positive 5 in this case. So complex numbers, graphing them in the complex number plane, very straightforward, and then finding their absolute values, also very straightforward. Cheers.